It also has known CFT data, so known OP coefficients and spectrum. And it also has a field theory, a Lagrangian description, semi-classical limit plus known. So that in this setup, we are able to compute correlators both via a conformal block decomposition and via a path integral. And we are able then to compare the two and understand in this context how single valuedness is restored. Okay, to be specific, we will consider a specific class of these correlators, so these heavy, light correlators. Let me denote them HH, LL. And here, yes, as I briefly mentioned, by heavy, I will mean operators which have a conformal weight HH with scales with a central charge, as we take this to be large. And by light, by a slight abuse of terminology, I will actually mean operators which are perturbatively heavy. So operators which still have a weight HL, which scales as a central charge, but such that the ratio HL over C is much less than 1. And so we will perform computations to leading order in the semi-classical limit. So I will not discuss the computation of quantum corrections to that correlator. So leading. And also for technical reasons, we will work in a linearized approximation in this ratio. And so let me just also briefly mention that well, the original motivation for looking at this particular type of correlators indeed was coming from holography, where this type of observables have been interpreted as computing the entanglement entropy of an interval in a state which is excited by the insertion of a heavy operator. Entanglement entropy. So at the level of the blocks, I think it has been kind of understood. I don't know if there is really a proof, but yeah, the blocks of Fitzpatrick, Kaplan, and Walters interpolate between the two regimes. At the level of this correlator that we are computing in Liouville, they are in a sense connected, but it's not really trivial, the connection. So that, well, maybe I will comment on it at the end. Okay. So before we start, maybe I will do a brief review of Liouville theory, of the ingredients of Liouville theory that we will need. Speed up. Okay. Okay, so Liouville theory is a two-dimensional conformal field theory. It has a central charge C, which is parameterized in terms of a parameter Q, or equivalently in terms of B. The semi-classical limit is defined by B going to 0, in which the central charge is approximately 6 over B squared. As I said, it has known CFT data. The primary operators our vertex operator, V alpha, where alpha is the Liouville momentum and phi the Liouville field, and it also has known oblique coefficients, C alpha 1, alpha 2, alpha 3, which are given by the famous DOZZ formula, which I'm not going to write. So the field theory, so the Liouville field theory is an interacting field theory of a scalar, which is linearly coupled to a background metric, and which has a exponential self-interaction. And here the coupling mu is positive. between saddles, we will also have a sum over them. Okay, so just to repeat, the correlator that we will compute is a correlator of 4 vertex operators which have momenta eta h over b, so the heavy one. And let me also take canonical insertions and eta l over b. We will also assume that both eta h and eta l are real. And eta l, being a perturbatively heavy operator, will be much less than 1. Okay. Okay, so for the solutions of this equation, and so for the saddle point approximation of this type of correlators, it is known that there exists a unique real and single-valued solution